Hey there, Dave here, taking a look at the puzzle from the Tuesday Tute. So let's dive right in and see how this goes. So this is what the Tute has sent along. They say, given the XOR truth table, and we get a truth table here for this binary connective that's written XOR, and they want us to develop introduction and elimination rules that are harmonious when added to the system NJ or NK or NM. And I'm going to assume that what that means is developing introduction and elimination rules that have some connection to this truth table, as well as being harmonious. Just because that seems to be probably what's intended. And then I'm meant to show that this is a derivable rule and what rules used to construct it. Is there a systematic way to construct derivable rules? So I'll talk a little bit about derivable rules once we get to that point, but let's just start out by thinking about this truth table and how we might relate it to introduction and elimination rules. So I'm going to move over here and let's get this truth table, and I'm just going to write the XOR as a binary connective, just as like a big X like that, just for simplicity. But let's get the table here, right? So we're going to look at, we're looking at some structure with two values, T and F. And the idea here is we're going to make this thing F when both its inputs have the same value as each other, when both its components have the same value as each other. And we're going to make it T when its components have different values from each other. So this is a connective that goes sort of true or false, depending on whether its inputs have different values or the same value. This is one, incidentally, if you think back to early in the semester when we were looking at the Boolean structure in the first place, this is the kind of thing that you'll see wired up. For example, if you want to make a light switch that's controllable from different locations, from say two different locations, right? So imagine the components here, the T and F on the left and the T and F along the top. Imagine those components are two different switches controlling the same light bulb. And then the result, that the actual value that the compound sentence takes is going to tell us whether that light is on or off. So imagine currently both switches are off, let's say, and this tells us that the light will be off. But you can see if we flip either switch, right, if we flip the switch on the left, we'll go from off to on. Or if instead we flip the switch on the right, we would also go from off to on. So we're actually able to change the light state from only one switch, no matter which switch it is. But that's not just the case if we start with both switches off. Actually, you can see by looking at this table, no matter where you start, if you're here at T, your two neighboring values are Fs. Or if you're here at F, your two neighboring values are T. Or just to complete the square, if you're here at T, your two neighboring values are Fs again. So what you get is no matter where you are, no matter what state the switches are currently in, you can change the state of the light bulb just by changing the state of one switch while leaving the other one alone. So if you have any lights in your house that are a single light controlled by two different switches in two different places, you can see that light as calculating this truth table, or the wiring going on behind that light is a way of calculating this truth table. So this is an interesting truth table. It tends to get called exclusive or just XOR, which the puzzle makers in this case have gone with the name XOR, so I assume they're familiar with it from that context. So first thing we need to think about, we've got this table, but what can this table mean? Right? Our connective tables are always in the context of some structure. Now, this puzzle hasn't given a structure to work with. I assume that we're looking at a two-valued structure because there are only two values here in this table. So I'm going to just kind of take my best guess and suppose that the idea is to add this binary connective to the Boolean structure, which is the main two-valued structure that we've looked at. So this is, again, just me filling in details of the puzzle, trying to kind of make the best go I can of it. So I'm going to talk about adding a connective. And again, I'll just write it as X to our language, and I'm going to suppose that this is a binary connective, because after all, we have a binary table here. So I'm going to add a binary connective x to our language, and then I'm going to add this table to the Boolean structure. Right, so now we get a larger structure, we get a structure that's like the Boolean structure, but it has this additional connective in it. So we're starting out by thinking about this structure. I'm actually going to go farther than that and not just think about the structure, but I'm actually going to think as well about the classical matrix on that structure. Right, so remember, we get to a matrix by adding to a structure some choice of which values are designated, and the classical matrix is the matrix we get from the Boolean structure by having as our set of designated values just the value t. And I'm going to do that because when it comes to thinking about introduction and elimination rules, and that's what this puzzle asks us to do, we often want to think about those introduction and elimination rules, in connection to some kind of logic. And if we just have a structure in front of us, we don't yet have a way of determining a logic. We need, well, we don't need a matrix, but if we're kind of coming via structures, we need to add something more to get to a logic, and a matrix is the way we've looked at to do that. So that's what I'm going to assume. So this is kind of me filling in enough background to try to get this puzzle to a state where I can approach it and answer it. So here's what I'm going to take us starting out from, is Boolean structure with this additional binary connective added to it. And I'm going to suppose that we're looking at a matrix over this structure that's like the classical matrix, right? That has just the value t as designated and not the value f. Now, with that all in mind, let's see. The puzzle says to develop the introduction and elimination rules that are harmonious when added to the system nj, nk, and m. Okay, so I'm going to focus on nk here. But before I do that, let me just tell you why I'm going to do that. I'm going to set nj and nm to one side and focus on nk. So the reason I'm going to do that is basically because of these assumptions that I've had to make to lay it out already. All right, so if you remember, nm is a proof system that determines a logic called minimal logic, and J is a proof system that determines a logic called intuitionistic logic, and NK is a proof system that determines classical logic. So because we're working with something a lot like the classical matrix, right? It's just the classical matrix augmented with this additional connective. It makes the most sense to me to start from thinking about classical logic, the logic that we would get from this matrix, and thinking about, okay, well, we want to add this connective to the matrix on the one hand. We also now want to add rules to our proof system on the other. So I want to start from a proof system that actually matches the logic that that matrix gives us, so that we can take a look at how to match this new connective using the rules over in our language. There are definitely interesting questions to be looked at, and it would not at all be a mistake or wrong to think about how we could add rules that would give us something like an exclusive OR connective in minimal or intuitionistic logic. But that's going to be certainly trickier, and it's not something I'm going to look at in this video, basically because the techniques that we need to use on the model side to capture things like minimal or intuitionistic logic are more complex. We won't do it with two-valued structures or two-valued matrices. In fact, it can't be done with two-valued matrices. So we will take a look actually in week 12's reading at a different way of providing models for intuitionistic logic. But for the purposes of this video, I'm just going to set nm and nj to one side, and I'm going to focus on how to add these to NK, classical logic, because that's what actually is going to match the classical matrix that we're looking at adding this into. Okay, so that's enough setup, enough background. Hopefully you've got a sense at this point of how I'm interpreting the puzzle and what I'm setting out to do. What I'm going to try to do is add rules to NK that are harmonious rules, which is one thing the puzzle asked for, but also so that the logic we get from nk plus these new rules is the same logic that we get by looking at the classical matrix plus this additional table for this binary connective. So let's see how we go with that. Actually, I'm going to scroll away, but as I do, I'm going to bring the truth table with us because I want to keep looking at that. Okay. So here we are. So now I want to think about introduction and elimination rules for this connective. So how are we going to proceed? Well, for an introduction rule, right, we're going to want, what would it take to be able to demonstrate phi x psi? I'm using the Greek letters here, right, because I want this to be for any sentences phi and psi. I want to think about what would it take for us to have a proof of phi x psi. And I'm going to get there by taking a look back at the table and saying, okay, what are the conditions under which this thing comes out to be true? And we see two different places it comes out to be true. And so I'll start thinking about it this way. This is going to be my first stab, and we'll see how it goes, right? I see that one way this sentence can come out to be true is here, right? If its left component is true and its right component is false. And so I'll say, well, here maybe is an introduction rule I could give for it, right? If I have some proof of phi and I have some proof of not psi, then putting those together, we can get a proof here. And let's call this the introduction 1, because as you might suspect, if this strategy works, I'm going to also need a separate rule to handle the other coordinate where it comes out to be true. So I'm going to have a second introduction rule, which I'll call creatively x introduction 2. And this will come from not phi and psi. Me phi, psi. Okay. Now I feel okay about these. We'll think a little bit about what we need to know, and what we can look at in order to see whether these work in a moment. But I'm actually going to, for now, hope that these work out well and move on and think about harmonious elimination rules. And then we'll come back once we have introduction and elimination rules both and think about how to connect this up to the sort of, to the model theoretic approach that we started from. So, got two different introduction rules. So now we want an elimination rule. And I'm going to do a little trick here to generate a harmonious elimination rule. And this kind of trick works pretty widely. There's limits to where it'll work, but I suspect it'll work here. Basically, the idea, if you want a harmonious elimination rule for some introduction rule that you have, often basically what you want to do is imitate the disjunction elimination rule. The disjunction elimination rule we have often gives you a nice clean pattern for elimination rules you can work with. This is a strategy for developing elimination rules. If you want something to Google and you're curious, this is something that's called general elimination. Anyway, here's what it will give us in this. I'm not going to do that step by step. There we go. Here's what it'll give us in this case. So I want to say, suppose I have some proof of this connective sentence. Now, if that proof came via an introduction rule, it had to be via one of these two introduction rules. So what I want to say is, okay, well, if it came from the first introduction rule, then that would mean that I could take for granted both a phi and a not psi. And so if taking those for granted could get me to some claim theta, then that would work out. And similarly here, right? So this is the same, but now based on the second introduction rule, and then the result will be theta. So this is my guess for X elimination. So let me just go over how I arrived at that and why it might be a sensible thing to think about. we want to say, okay, what can we prove from this sentence, this compound sentence, from phi x psi? And in general, the idea behind harmony is we want to be able to prove from a sentence whatever we can prove from the grounds for that sentence. And by the grounds for that sentence, I mean whatever we use in the introduction rules to establish that sentence. So I want to be able to prove theta from that sentence. That is, I want to be able to get to theta at the end. Exactly when I can get to theta from each of the possible sets of grounds that we could have used in an introduction rule to establish the compound sentence in the first place. Right? So in other words, in this sort of first subproof, I'm going to allow myself to discharge any open assumptions of either phi or not psi. And in this second subproof over here, I'm going to allow myself to discharge the reverse assumptions, any assumptions of not phi or psi. And if you compare that to the way our disjunction rules work, you see disjunction also has two introduction rules. It has an introduction left rule and an introduction right rule. Each of those only has one premise, right? Whereas here our exclusive disjunction that we're looking at here, each of the introduction rules has two premises. But similarly to our normal disjunction, right, there are two different introduction rules, and similarly to our normal disjunction, what we get in the elimination rule is this kind of, you have to consider if it came from one introduction rule, and you also have to consider if it came from the other introduction rule. So that's the basic strategy that I'm pursuing here. Now, again, we got to get back to the models at some point and see that this works. But what I'm going to do first is just check to make sure that these rules are actually harmonious, so that we can see what a reduction procedure would look like on these rules. See how that works. I'm pretty confident that these rules will turn out to be harmonious. I'm maybe less confident that they're going to hit the model spot on, but I guess we'll see how it turns out. So let us think about harmony. I'm going to just zoom out a little if I can to try to buy myself some more space. Okay, so how are we going to get a detour out of these rules? Well, it's going to have one of two forms. Right? Remember, we're going to get a detour when we introduce the connective and then immediately use it as a major premise for elimination. That major premise meaning it's over here, it's this left premise in the elimination. And since we have two different introduction rules, there are going to be two different possible ways that could go. Right? We might have used the first introduction rule, or we might have used the second. So let's suppose we used the first one. Right? So all we know is we've got some proof, and somewhere in it, there's some use of the first introduction rule here, where the formula it introduces is then immediately that major premise for elimination. We don't know where in the proof this happens. We don't know what sentences this involves, right? All we know is we've got some proof, and that happens somewhere in it. So what should that look like? What are we going on here? Well, we know we're going to have a phi and a not psi that come together in this one intro rule to give us phi x not psi. And we know that that itself then stands as that major premise for elimination. Phi not psi. And there's some formula theta that's being proved by that elimination. That's a very bad psi. Let me make that psi better. There we go. Theta, and that gives us a theta. But now let's think about the pieces of proof that we have together here, right? So we have this bit of proof that came from somewhere. We don't know where, we don't know what, right? There could be anything living up here. We have this bit of proof, and that too came from somewhere. We don't know where. And then what are we doing with this theta? Well, we don't know, right? There might be some more proof living off down here. Some way to go there. And now let's think about what other resources we have. Importantly, and this is the one I'm going to focus on, right? We have this block right here. And that is a block that's going to tell us how to get to a theta, potentially starting from some of these discharged assumptions of phi and not psi. And actually for this reduction, I'm just going to completely ignore what's going on over there. I don't care. So let's think about how we could take these pieces that we have and rearrange them, put them together in a way that gets rid of this detour, but still gives us everything we want, still gives us a proof that is a proof of any argument that our original proof was a proof of. So the core of it is basically going to be, that's a copy thing. How do I paste? No, I don't know how to paste. So instead, I'll just drag that over here and remember where it came from. So that's going to get us a theta, but we don't just want to get to theta, we wanted to do something with the theta. So what we'll do with that theta is just whatever it was we wanted to do with the theta. So this, what we have here now, is pretty good, right? This is bits of proof that we started with, so they must be good bits of proof. It gets us to whatever conclusion the original one got us to, because that's sort of down here on the bottom. We don't know what the original conclusion was, but whatever it was, we brought it over. The only problem here is these assumptions, right? We have these potentially discharged assumptions marked, but they were discharged by this rule here, by this rule of X elimination. And we've gotten rid of that rule of X elimination, bringing it down here. So those assumptions might no longer be discharged. And that would be a problem. Remember, part of what we need to do is make sure that we're not introducing any new open assumptions. So because these were discharged in the original proof, they were not open assumptions in the original proof. So we want to make sure that they're not open now either. So on its own, that isn't enough, but we do have the resources it takes to make that happen. In particular, we have this proof of phi that we can just plug in over there wherever we need a proof of phi, or wherever there used to be a discharged assumption of phi. And we have this proof of not psi, and we can plug that in over there wherever there used to be a discharged assumption of not psi. So the result might look a little bit messy on the page. That's just because my handwriting's messy, but hopefully you see the transformations we've done. This is actually very, very much like the way we would handle a disjunction reduction in NJ or NK or NM or any of our ordinary systems. The only difference here is that we've had to sort of bring over two different proofs and plug them in at the top rather than just one like we would with normal disjunction. So reduction is worked out for that first case, right? For the case where we use the first introduction rule followed by the second introduction, followed by the elimination rule. So now I'm just going to hit undo a whole mess of times to see if I can put back together our original proof there, and then remove some of my scribbles on it. There we go. There we go. Okay, so now I want to think, what happens in the other reduction case, right? We're not using our first introduction rule. Ooh, stretchy negation. Stretchy negation. Okay, I'll get rid of stretchy negation. But where we're using our second introduction rule. And the idea here is going to be exactly the same, right? We have some bit of proof here. That came from somewhere, we don't know where. We have some bit of proof here. That also came from somewhere, we don't know where. We're going to do something at the end of the day with this theta down here, but we don't know what. And now we're going to ignore this one and draw on this one. Right? And hopefully you can see that we have the materials again from our same starting points. Right now we're going to take this proof of not phi, whatever it is, and plug it in up top here wherever there's a discharged assumption of not phi. We're going to take this proof of psi, whatever it is, and plug it in up here wherever there's a discharged assumption of psi. And we're going to take whatever we were going to do with theta before and do it with this theta instead. And you'll see again the result will be a proof that has the same conclusion, same bottom, has no more open assumptions, right? Whatever is open up here remains, but nothing new has come in. Anything that's open here also remains. right? But the only sort of risk of creating new open assumptions was with these discharged ones, and we've managed to fill those in with materials we have. So again, reduction works out that way. So this elimination rule really is harmonious with our two introduction rules that we began with. So that's what I'm going to go with for rules for these, right? We've taken a look at these harmonious rules. Now I want to think about the connection between this and our original truth table. And here there's two sorts of things we want to think of, right? So we've got, on the one hand, we've got a sort of classical matrix plus this X connective given by this new truth table. And on the other hand, we've got NK, this proof system, plus our new rules, right? XI1 and XI2 and XE. And we want to think about the relationships between a model theory and a proof theory like this. What we want to do is think about the logics that they determine, respectively. So we know that the classical matrix on its own brings us to classical logic. And we know that NK on its own also brings us to classical logic. So we need to think now about these additions of this new connective and how that works. And there are basically two, well, let me divide the question that we want to ask here into two parts. So let's start, let's set the logic CLX set CLX to be the logic determined by the classical matrix plus this new truth table X that was given to us in the puzzle, right? So whatever logic that is, whatever logic that is, we'll call it CLX. So an argument is valid in CLX when it has no counterexamples in this matrix that we've come up with. And now we have this proof system over here, and I'll call this proof system NKX. And so now I'm going to split us into two questions. One is, can NKX prove every CLX valid argument? And this is a question that would go under the name completeness. Right? If we're asking if a proof theory is complete for a model theory, what we're asking is whether it can prove every argument that's valid in the model theory. And a second question we might ask is whether that proof system proves only CLX valid arguments. That is, suppose we do manage to come up with a proof of an argument in this proof system NKX, is there a guarantee that that argument is CLX valid? And this is what's ordinarily called soundness. And I will tell you, for purposes of this video, I see time getting a bit long, I am not going to tackle this first question, this completeness question. Completeness proofs can be kind of routinized, but they can get a bit hairy, they can get a bit long, they can get a bit involved. And yeah, it's kind of too much for this context. But what I will do is take a look at this second question, at this soundness question, because that's probably going to be more tractable. And it'll at least give you a sense of the kind of reasoning that would go into this sort of thought. So what we want to do now, start by thinking just about NK. Well, NK is only going to prove things that are classically valid, and those things are all going to be CLX valid as well, basically because if we had a CLX counterexample to these classically valid things, then that would just be a classical counterexample to them as well. So we don't really need to worry about the NK part of NKX for purposes of this question, what we really need to focus on is the new rules and make sure that the new rules will only allow us to prove something if it's actually CLX valid. So let's take a look, for example, at our X introduction 1 rule. I think this is the one I called X introduction 1, and it's the one I'm calling 1 now anyway. So let's think about this rule. And let's think about what this rule is in effect telling us in context, right? It says if we have a proof with conclusion phi, and we have another proof with conclusion not psi, then we can put them together using this rule and create a new larger proof of phi x not psi. So let's suppose that our starting proofs, the two proofs we start with, are only proofs of CLX valid arguments, right? So let me actually indicate some assumptions now of these starting proofs, and I'll just put gamma for the assumptions because we don't know what assumptions they are. But gamma here is the open assumptions. So think, what arguments is that a proof of? Well, that's a proof of every argument that has a conclusion psi, and that has everything in gamma among its premises. And similarly, let's think about what this second proof is that we start with. I don't know, I'll use delta for it. So what arguments is that a proof of? Well, that's a proof of any argument that has its conclusion not psi and has everything in delta among its premises. So if those already worked, right, then all of those arguments need to be CLX valid. So in particular, this will tell us that this argument, which has gamma exactly as its premises, which is one way of having everything in gamma among your premises, right? So let's suppose that that's CLX valid. And similarly, we're going to suppose that this is CLX valid. Because what we want to do is make sure that this rule doesn't create any new problems for CLX validity, right? If it takes as inputs things that are CLX valid, can it give us as outputs anything that isn't, or will it actually hold only to CLX valid things? So we want to ask now, given these as input, can we say that this larger argument is CLX valid, right? If we knew that those smaller arguments were CLX valid, would it be enough to say that the larger one is CLX valid? If so, then we know that this rule hasn't brought us outside that sphere of soundness, right? This rule won't have brought us any new proofs of things that are not CLX valid. Any such proofs would have to come from somewhere else. So now this allows us to work back in our land of our matrix, right? We're thinking about our classical matrix plus X here. So since we know the first argument is CLX valid, right, we know that if for any valuation V, we know that if the valuation, I'll just put that to mean that the valuation of everything in gamma is true. If the valuation of everything in gamma is true, then the valuation of phi is true. That's what we know from our first argument being CLX valid. We also know from our second argument being CLX valid that if the valuation of everything in delta is true, then the valuation of not psi is true, which is to say the valuation of psi is false, right? Because we're working, again, with that extension of the Boolean structures. So we know how negation works in the Boolean structure. So this is just what we get told by that first argument being CLX valid, which we've assumed. And this is what we get told by that second argument being CLX valid, which we've assumed. So now let's think about our question here, right? Suppose that everything in gamma is true and everything in delta is true on a particular valuation, well, then what do we know? Then we know from our first argument that the valuation of phi is true, and we know from our second argument that the valuation of psi is false. And that, if you go back and check our XOR truth table, which you should be able to see on the left-hand side of the video poking in there, you should see that will be enough to tell us that the valuation of the compound sentence in this case is true. And that's indeed exactly what we need to be sure that this argument comes out CLX valid. So there's a step of reasoning that we've given there. We would need to go through similar reasoning for the other introduction rule as well as for the elimination rule, right? We've added 3 rules and we need to make sure that all of them can only result in arguments that are, only result in proofs of arguments that are CLX valid. I'm not going to go through that reasoning for each of those rules, but for this first rule, hopefully that gives you a sense of what the reasoning would look like that we want to do to go through. Okay, so let me, with that, return back to the original puzzle. And the original puzzle wants us to show that this is a derivable rule and what rules you used to construct it. Is there a systematic way to construct derivable rules? And here, so derivable rules have come up in a puzzle or maybe 2 puzzles on the forum. They're not something we've talked about in detail in the class. They're not something that the readings go over. So let me just give you a quick view of what derivable rules are, because I assume that this question, this puzzle, is drawing on that notion of derivable rules that we've looked at in some of the puzzles. So think, for example, about the following rule, or I'll give you an instance of a rule. Looking at that rule, right, that looks like a rule. It's got a shape of a rule. Think about NM, NJ, NK, doesn't matter. They're all going to play the same for this particular case. That is not a rule in any of these systems, right? There is no rule that allows us to move directly from that first sentence to the second one in any of these systems. However, there's something that the systems kind of endorse or implicitly endorse that we can see as importantly related to that rule. So imagine we have the same starting point, but now we use a conjunction elimination on the right, and that would give us P and Q and R, and then use a conjunction elimination on the left to get to P and Q, and then use a conjunction elimination on the right to get to Q. So you can see that although we have no single rule that allows us to do that manipulation in one go, we do have rules that in combination can be used to get from that starting point to that finishing point. It just takes a few different rules, takes a few steps along the way. When that happens in a proof system, what you say is that this rule, the one that is not actually part of the system, is nonetheless derivable in the system. Right? So it means that you can make within the system any manipulations that it would allow you to make. It's just that it might take you a few extra steps to do it. This can be interesting to think about for a number of reasons. It kind of comes up in a range of different ways. So returning to the question here, show that this, and I assume by this is a derivable rule, it means the rules that we came up with for this connective are derivable rules. And of course, being derivable, you always have to be derivable in some system or other. In this case, since we were thinking about adding these to NK, I'll take this to show that this is a derivable rule in NK. But the answer here is going to be pretty straightforward. It's not. The rules that I gave for this X connective are definitely not derivable in NK, because NK has absolutely no knowledge of this X connective at all. NK is a proof system for a language that doesn't even contain this X connective. And so certainly there will be no way to derive the rules that I've given in NK or NJ or NM or any of those systems, because the rules that I gave here do involve this new connective. And so if we wanted to derive these rules, we would need to derive them from something that also involves this new connective. So yes, so I will rather than showing that these rules are derivable, explain why in fact they cannot be derivable. Is there a systematic way to construct derivable rules? Just to finish, basically, yeah, right? So given a proof system anyway, you say, okay, well, look, all the rules that occur in the proof system, those are all derivable, kind of trivially, right? Derivable from themselves. Okay, so that covers it. But now think about all the two-step combinations you could make, right? So imagine we could have a proof that has a conjunction elimination on the left, followed by a disjunction introduction on the right. That's one two-step combination we could look at. Or we could look at a conjunction elimination on the left, followed by an implication elimination. That's another two-step rule we could make. Or we could look at a conjunction elimination on the left, followed by a fulsome elimination, so on. And so on, right? So you can look at all the two-step rules you can make. So, for example, if we had fulsome and any sentence phi, then conjunction elimination on the left would give us a fulsome, and then fulsome elimination could give us any sentence psi. So here's a derivable rule in nj, for example, because nj has both of those rules, right? Here's a derivable rule that we can get going. And you can imagine every possible combination of two rules in a row and all the results of those. And then you could think of every possible combination of three rules in a row and all the results you would get from those, every possible combination of four rules in a row, of five rules in a row, and so on. So this would actually take you a very long time to do it, but it's certainly systematic, and it would in the end get you every derivable rule if you're willing to accept, by in the end, I mean it'll take you an infinite amount of time because there are infinitely many derivable rules typically, certainly for systems with any degree of complexity like these. So yes, there is a systematic way, maybe not the most satisfying one, but systematic ways are very rarely satisfying. They often are just check every combination and there you go, and indeed that's what I'm going with here. So that's what I'm going to do for this puzzle today. Thank you very much to the puzzle makers. I hope this is of some interest to you and of some use to you. Let me just return to the rules there to close with, right? So the idea was to come up with rules that capture that table. Here are rules that I haven't shown capture that table in full because that would be a seriously in-depth thing to do, but I have shown at least that these rules are harmonious, and we've looked through the details seeing that that first rule is at least going to remain sound for what we're after, and I certainly believe that the other rules will remain sound as well, although I haven't checked the details on that here. So thanks very much to everyone in this Tute for coming up with this puzzle. I hope you are having a lovely day, and I will see you when I do. Bye-bye.